This is problem-solving techniques, and we're looking at the gravitational chapter. And the interesting thing with the gravitational chapter is we have all of these equations. Now, in terms of problem-solving techniques, all year long we've been using the guess method, and the guess method is truly valuable. It's going to help you figure out which equation to use. In particular, that unknown part, identifying it correctly, identifying the givens correctly, will enable you to choose which equation to use. Once you get the equation chosen and you have all the givens identified correctly, then it's usually fairly easy. But identifying those givens correctly can be tricky. And to do that, you're going to need to visualize what's going on. Sometimes the visualization is simple, other times it's not so simple. When it's not simple, I strongly recommend labeling the diagrams. In particular, the period one, the velocity two, those guys really need to be visualized strongly. Free body diagrams, wonderful as they are not really very helpful in the gravitational unit, so they don't come into play very much. Not listed as a problem-solving technique, but incredibly valuable, is knowledge. Knowledge of what all of these equations mean and what they're good for, something we covered a bit in last night's video. Kepler's law, again, is that ratio. You have to have two objects orbiting the same thing. Newton's law of universal gravitation is universal, works everywhere. Sometimes you don't have all of that information, but it's a universal gravitation. Realize that Newton's law of universal gravitation is another way of finding F sub g. So F sub g equals m1g is the same as F sub g equals big G m1 m2 over r squared, except that little g is site specific. So you can't use little g everywhere. 9.8 can only be used on the surface of the Earth. Big G and universal law of gravitation can be used everywhere. This guy over here can be used if you have the appropriate information and can find little g for that particular planet. So if you're going to use this formula up here to find little g, then you can use this guy for the little g in that situation. Okay, the other three are specific. One is for finding period. When you don't have something to compare it against, like with Kepler's law. So if you just have information about the object doing the rotation and the object it's rotating around, then you're going to have to use this version up here. Likewise, for velocities, you have to be careful between the two. Remember, the one with a 2 in it is to escape, and that's the escape velocity. The one without the 2 is just the orbital velocity. Okay, so we've got Kepler's law, which is a ratio thing. Units don't matter as long as they're the same. We've got these three that are kind of interrelated. They all deal with force of gravity and little g. And then we've got the specifics, the period and the velocity equation. So let's take a look at a problem. What is the velocity of a satellite that is 300 kilometers above the surface of the Earth? Now we're asking for a velocity, so we're going to be using one of the two velocity equations. It doesn't say escape velocity, so we're probably going to be using this guy. So I can write the equation out right away. What information do I have in the problem? Not a heck of a lot. Certainly not enough to do this. I've got 300 kilometers above the surface of the Earth. So if I draw a picture now, if I start to visualize, I've got the Earth, I've got some Earth radius, I've got the Earth's surface, and then I've got this planet, or sorry, this satellite that is above the Earth's surface by 300 kilometers. That 300 kilometers, that's not the radius, that's just the distance above the Earth. So I need to know the Earth's radius, and also I've got this mass thing in here. And it's a big mass, so that's the Earth's mass. So I need to get that information. Okay, I looked up that information. The planetary radius of the Earth is 6,300 kilometers, and the mass of the Earth is 5.97 times 10 to the 24th kilograms. You should write this down because you're going to need that information too. Once we have that, realize the planetary radius is this right here. That is not this r. This r is the distance from center to center. And the distance from center to center is from the middle of the Earth to the middle of the satellite. So I need to take this 6,300 kilometers and add to it the distance that the satellite is above the Earth. So that's an easy add. R is going to equal 6,600 kilometers. After that, I'm going to have to change that kilometers to meters. I've got the mass of the Earth, and that's that big M. Big M is 5.97 times 10 to the 24th kilograms. I've got enough information to solve this problem. So you can go ahead and solve it at another point in time. Next one. An asteroid is in Earth's orbit. The people of Earth wish to colonize it, but are concerned about the gravity on its surface. It has a mass of 2.4 times 10 to the 24th kilograms and a radius of 2,500 kilometers. Find the magnitude of gravitational field, so they can decide if they should colonize the asteroid or not. Well, when we're asking for the magnitude of gravity, the gravitational field, we're not looking for F sub g. That would be the force of gravity, so that's not what we're looking for. So what are we looking for? Gravity on its surface, we're looking for little g. Little g equals what? Okay, once we know what we're hunting for, then on this one it's pretty easy to find the formula that we're going to be using. So we're going to use that formula. To use that, we have to know big G. Well, that's okay. That's a constant. We've got that. We've got to know big M. What is big M? M is the mass that you're standing on. And we've got that information, mass of 2.4 times 10 to the 24th kilograms. And then we need R. R being the distance from center to center. Will the planet's radius work? Well, we're talking about this asteroid, and we have the radius of the asteroid, and we're talking about what G is on the surface of the Earth. So if you're on the surface, or the surface of the planet, if you're on the surface, that is the radius. So yes, that radius will work. Note that it's kilometers, and you're going to have to change that. Otherwise, it looks pretty straightforward. What is the mass of planet X if it has a moon with an orbital period of 5 days and an orbital radius of 4.5 times 10 to the 4th meters? So I'm hunting for the mass of planet X. And I've got a moon, and that moon has a period of 5 days, and it's got an orbital radius, not a planetary radius, but an orbital radius of 4.5 times 10 to the 4th meters. Now, I'm going to draw it real quick just to make sure. I've got some planet X, and I've got some moon going around it, and it's got this orbital radius r. Okay, I'm hunting for the mass. I've got period. Well, I only have two equations with period in it. I've got Kepler's law, and Kepler's law has no mass, so that's out. And then I've got this guy down here. Let's see, this has period in it, so that's good. It has big G, well that's okay, this is a constant. It has big M. Big M is the mass of the planet that you're orbiting around, which is what I'm hunting for, so that'll be good. Now do I have R? R is the distance from center to center, that's that orbital radius, so that equation's going to work. So I can use this big equation, big T equals 2 pi r cubed over big G, big M. Now the issue is period has to be in seconds. This is in days. So I'm going to have to convert that to days before I try and plug it in. Radius has to be in meters, and it is, so we're good. So I just have to convert that days to seconds, and then we should be good and you can solve it. Next one up, what is the mass of planet X if it has a satellite orbiting at a velocity of 2.8 times 10 to the 3rd meters per second, and it is 4.3 times 10 to the 7th meters from the velocity of planet X? I'm hunting for mass again, and the mass of planet X. I have a velocity, and I have a distance from the center velocity, I've only got two equations with velocity in it. Both of them have mass in it. This guy is escape velocity. It's got the 2 to escape, so I'm not going to use that one. So I'll use this. And after that, it's fairly straightforward. My velocity units are in meters per second, which is good. And my distance from the center is in meters. That's good. Everything looks fine for using that equation. Calculate the period of Saturn as it orbits the Sun. It is 9.14 Earth orbits from the Sun. So I'm hunting for period. I have two equations for period. This one and this one. It does not give me any masses. I need the mass of the Sun. It does not give me any distances, except it kind of does. It gives me the distance of Earth orbits from the Sun. Well, without looking up any other information, I could use Kepler's laws. So, I'm hunting for the period of Saturn. I know that the radius of Saturn is equal to 9.14 Earth radiuses. I know the period of the Earth is equal to 1 Earth year. I know the radius of the Earth is equal to 1 Earth radius. With that information, I can go ahead and solve this. Now, these are actually problems from the worksheet that's going to be handed out to you, and this information is not on the worksheet, so you need to write that down. Hopefully this is a good overview for you, so you can start thinking of how you're going to solve these problems. Have fun with the worksheet. Thank you for your time.